All right, and now moving on to the last lesson in this video, 9.3, we're going to talk about Gibbs free energy. And Gibbs free energy is essentially asking us, will a reaction happen on its own? So we use delta G, which is the change in Gibbs free energy, to determine whether the reaction will be spontaneous or not spontaneous. And in this lesson, we're going to start using the term thermodynamically favored, meaning that a reaction can occur without any outside energy input. You might hear the word spontaneous, but in AP chemistry, they do prefer thermodynamically favored because it doesn't mean the reaction happens instantly. It just means that it's energetically possible. So moving forward, we're going to connect enthalpy and entropy to determine Gibbs free energy and predict whether reactions are favored or not. One way to calculate Gibbs free energy for a physical or chemical process is by using the standard Gibbs free energy of formation values. And by using those values, we can get the overall Gibbs energy for that process. And it's the same process when we are solving for delta S of a reaction or delta H of a reaction. We're going to take the total sum of our change in delta G for the products, and we're going to subtract the sum of our delta G for our reactants. And then another way to solve for delta G is by using our enthalpy, our temperature, and our entropy of a system. And that is using the bottom equation there, delta G equals delta H minus T times delta S. And then the last part of this lesson is talking about how temperature affects whether a reaction is thermodynamically favored. So instead of always calculating delta G, we can also just look at the signs of delta H and delta S. If delta H, or the change in enthalpy, is negative, and delta S, or the change in entropy, is positive, that's our best case scenario, right? Because we know if delta H is negative, it's exothermic. If delta S is positive, that means that we have an increase in disorder. So those two things are pointing in the direction of a spontaneous or thermodynamically favored reaction. If delta H is positive and delta S is negative, so now we have an endothermic reaction, so energy has to be put in, and we have delta S is negative, which means we have a decrease in entropy, which means we have more order. Those are two things that are telling us this is probably not going to happen on its own. So that is not going to be thermodynamically favorable. Now for our middle cases, let's say both delta H and delta S are positive, the reaction is only going to be favored at high temperatures, whereas if we have both our delta S and delta H negative, then the reaction is only going to be favored at low temperatures. So this table is a very powerful shortcut to have in your notes if you don't always want to calculate delta G. All right, so what does it mean for a reaction to be thermodynamically favored? Well, that is going to tell us that a reaction is going to proceed under a given set of conditions, and two factors are going to affect that, enthalpy and entropy. And those are two things that can drive a chemical reaction into thermodynamic favorability. So first, let's talk about enthalpy. We know that a negative enthalpy is thermodynamically favored because it means the reaction is going to release energy to the surroundings, making the system more stable. And systems naturally move towards lower energy states, so losing energy is going to be favorable. This energy release also helps drive a reaction forward without requiring any additional input of energy. So a negative delta H, or an exothermic reaction, is going to drive a reaction to thermodynamic favorability. Then talking about entropy, high entropy is thermodynamically favored because it's statistically more probable. So systems naturally evolve towards states with a high number of possible arrangements and spreading out energy and matter. And that is going to go back to the second law of thermodynamics, which dictates that spontaneous processes increase the total entropy of the universe. So a high entropy system can drive a chemical reaction into thermodynamic favorability. So that means if both of these conditions are met, meaning we have an exothermic reaction and we have an increase in entropy, that means that no matter what conditions we have, the reaction is going to be thermodynamically favorable. So at all temperatures, if we have a negative delta H and a positive delta S, we are going to have thermodynamic favorability. Now, in opposition to that, if our enthalpy is positive, meaning we have an endothermic reaction, and then our delta S is negative, meaning we have a decrease in entropy, that means that the reaction is never going to be favored at any temperature. It doesn't matter what set of conditions you have, there is nothing that we can do to make that reaction thermodynamically favorable. All right, so we know a negative delta H and a positive delta S can spontaneously drive a chemical reaction. But what happens if only one of those conditions drive a chemical reaction? And how do we determine what sets of conditions actually make a spontaneous reaction? Well, let's start off with this chemical equation here. We have solid carbon or coal reacting with water vapor to form carbon monoxide and hydrogen gas. Now, just by looking at this chemical equation, I can see that I have 1 mole of gas as a reactant and I have 2 moles of gas as a product. So thinking back to entropy, I know I'm going to be increasing entropy because I'm increasing disorder of a system by doubling the number of gas molecules. So just by looking at this equation without giving me any detailed information, I already know that this is going to have a positive delta S, or an increase in entropy. I also know that carbon monoxide is a very toxic gas, and if I take coal and soak it in water, it doesn't automatically form carbon monoxide gas. So I am assuming that this is going to be an endothermic reaction, meaning I'm going to have to put energy into it to actually kickstart this reaction. All right, so for this equation, we are given a positive delta H and a positive delta S. The positive enthalpy means that the reaction requires energy input or is endothermic, which is not favored. However, the positive entropy means that the system becomes more disordered, which is in fact favorable. So when we have these two conditions and we are at a low temperature, that means the energy requirement, or delta H, is going to dominate, which tells us that the reaction is not going to be favored. However, if we have these set of conditions occurring at a high temperature, the importance of increasing disorder becomes stronger and outweighs that energy cost needed. So the reaction becomes overall thermodynamically favored. Now let's look at a chemical reaction that can be driven towards thermodynamic favorability through enthalpy. So just by looking at this equation, you can see that we're starting with aqueous ions as our reactants, which are free moving and very dispersed. And because they have more possible arrangements, that means they have a higher disorder. Then moving into our product, we can see we are forming solid silver chloride, which is a solid precipitate, and particles are going to be locked in a fixed structure, which is therefore a low disorder. So because we are going from high disorder to low disorder, this is going to tell us that the entropy is decreasing. So we're going to have a negative delta S. Now, the negative enthalpy means that this reaction releases energy, which is favorable. However, the negative entropy means the system becomes more ordered, which is unfavorable. So at low temperatures, the energy release is going to dominate, so the reaction is going to be favored. However, if we have this reaction occurring at high temperatures, the importance of the decrease in entropy becomes stronger and outweighs those energy benefits, so the reaction is not going to be thermodynamically favored. Now, let's talk about Gibbs free energy. So, everything we just talked about with thermodynamic favorability is Gibbs free energy. It is what combines enthalpy, entropy, and temperature to predict whether a chemical or physical process is spontaneous or thermodynamically favored. Delta G is going to represent the maximum amount of energy available to do work from a chemical or physical process at a constant temperature and a constant pressure. So if we have a negative delta G, that is going to tell us that the reaction is thermodynamically favored. If we have a positive delta G, that means that reaction is not going to be thermodynamically favored. On the AP Chemistry exam, there's going to be two different scenarios in which you are solving for delta G. And the first scenario is when you are given Gibbs free energy values for all the substances in your chemical equation. And in that case, you're going to be using this top equation here, where you take the sum of your Gibbs free energy of your products and subtract the sum of your Gibbs free energy of your reactants. And that is the same process that we have used for solving for delta S with entropy values and delta H with enthalpy values. Now, this equation here, delta G equals delta H minus T times delta S, is what we're going to use to really understand all of the scenarios that we just went over. And if you are taking notes, I highly recommend writing in this table here, which summarizes all of the four scenarios in relationship to delta H and delta S and how that affects delta G. So now that we have this equation here, I would like to go back through the two examples that we did when both delta H and delta S are positive and when they are both negative. And I want to go a little bit more in depth using this equation. All right, so in this example, both of our values were positive. So let's talk about why at certain temperatures this can be thermodynamically favored and at some temperatures it cannot be. So starting with our equation, delta G is equal to delta H, which we know is positive 131 kilojoules per mole. Then we're going to subtract our temperature, which right now we don't know. That's going to be in Kelvin, times our delta S. But notice delta H is in kilojoules per mole and delta S is in joules per moles times Kelvin. So we need to get that joules into kilojoules if we want the units to check out at the end. So to do that, to go from joules to kilojoules, we're going to divide by 1,000. So this is going to be positive 0.134 kilojoules per mole times Kelvin. And as you can see with our units here, those temperature units are going to cancel out when they're multiplied. And then we're just taking kilojoules per mole and subtracting kilojoules per mole. So delta G will be in kilojoules per mole. So now let's talk about why temperature is important in this scenario. So let's say we're at room temperature, which is 25 degrees Celsius. That is 298 Kelvin. 298 Kelvin times 0.134 kilojoules per mole times Kelvin is going to give us 39.932 kilojoules per mole. And we know for our delta H, we have 131 kilojoules per mole. So when we subtract that, we're going to end up getting positive 91.068 kilojoules per mole. And as talked about 2 slides ago, we know that if we have a positive delta G, that is not going to be thermodynamically favorable. So now let's talk about what happens when we increase the temperature. So let's increase the temperature of this system to 1200 Kelvin. When we increase to 1200 Kelvin and multiply that by 0.134, that's going to give us a T delta S at 160.8 kilojoules per mole. And we know we started with a delta H of 131 kilojoules per mole. So when we solve for delta G, we're going to get a negative 29.8 kilojoule per mole value. And because it is negative, we know that now at 1200 Kelvin, we have a thermodynamically favorable reaction. And that is why when we have a positive delta H and a positive delta S, it's only going to be thermodynamically favorable when the temperatures are extremely high. And now let's look at an equation where enthalpy is going to drive our reaction towards thermodynamic favorability. So here, both our delta H and delta S values are negative. So let's go ahead and plug those into our delta G equation and figure out which temperature is going to be more favorable. So we have delta G, that's going to equal delta S, which is negative 63.5 kilojoules per mole, minus T delta S, so T is going to be in Kelvin. Delta S is negative 343, which we need to convert to kilojoules, so it's going to be 0.343 kilojoules per mole times Kelvin. So now let's start with our high temperature. So let's use 1200 Kelvin again. If we had 1200 Kelvin times our negative 0.343 kilojoules per mole, that's going to give us negative 411.6 kilojoules per mole. And if we take our original negative 63.5 kilojoules per mole and subtract that number, we can very clearly see that we are adding 411.6 to that negative 63.5. And that is going to give us a value of positive 348.1 kilojoules per mole. And we know if we have a positive value for delta G, it is not thermodynamically favored. So we know if both delta H and delta S are negative, a high temperature is going to make this equation or this system not thermodynamically favorable. So let's go to low temperatures. Let's say we were at a very low temperature of 100 Kelvin. By multiplying our T times our delta S, that is going to give us a negative 34.3 kilojoule per mole value. And if we take our original delta H, 63.5 kilojoules per mole, and we subtract that number, we're going to end up getting a value of negative 29.2 kilojoules per mole. And because this delta G value is negative, in this specific case, at a very low temperature, this system is going to be thermodynamically favored. So recap for this one, if delta H is negative and delta S is negative, it's only going to be favorable at low temperatures. All right, so this question says the chemical equation above represents the exothermic reaction of methane and oxygen gas. Which of the following best helps to explain why the reaction is thermodynamically favorable at 2000 degrees Kelvin and 1 atmosphere of pressure? Now we know from our trend, if we're looking at the trend specifically, if we have a negative delta H and a negative delta S, that trend tells us that it's only favorable at low temperatures. However, I want you to notice our very large negative delta H value, meaning it is very exothermic. And look at our delta S. It's really small comparatively to that delta H value, meaning if I were to convert that to kilojoules per mole times Kelvin, that's going to be negative 0.005 kilojoules per mole times Kelvin, which means is if my temperature is actually going to do anything to this delta H value, it has to be enormous. So the question is saying, which of the following helps explain why the reaction is thermodynamically favorable at 2000 Kelvin, even though the trend is telling us that this should only really be favorable at a low temperature. So let's plug that into the equation. So delta G is equal to delta H, which is negative 803 kilojoules per mole, minus our temperature, which is 2000 Kelvin, and our delta S in kilojoules, which would be negative 0.005 kilojoules per moles times Kelvin. So this value on the bottom here is going to give us negative 10 kilojoules per mole. And then we have our original 803 kilojoules per mole minus negative 10. So that's going to give us negative 793 kilojoules per mole. So as you can see, even though we were at a actually a very high temperature of 2000 Kelvin, it really didn't budge our delta H because of how drastically different our delta H and our delta S is. So this is in fact kind of an outlier in the trend, and the trend still applies. It's just so drastically different that the temperature would literally have to be over 160,000 Kelvin for it to be not thermodynamically favored. All right, this next question says the oxidation of iron is represented by the chemical equation above. Which of the following correctly explains whether or not the reaction is thermodynamically favorable? So looking at the equation, you should be able to identify whether delta S is positive or negative. And we see that we have solid and a gas forming just a solid. So we're going from 3 moles of gas on the reactant side to no gas on the product side, meaning we are increasing order or decreasing disorder, which means we're going to have a negative value for delta S. And we know if we have a negative value for delta S and a negative value for delta H, we're going to have thermodynamic favorability only at very low temperatures. And our last example for this lesson, a standard electrochemical cell is constructed according to the diagram, which I did take out because we haven't learned that yet and it gets confusing. A balanced equation and thermodynamic data are provided for the reaction that occurs while the cell operates at 300 Kelvin. So for this type of question, you do not need to look at the cell diagram, so we're just going to save that for when we actually learn about cell diagrams. So the question is asking, what is the approximate value for delta G of the reaction at 300 Kelvin? So you are just plugging this into your delta G equation. So delta G is equal to delta H, which is negative 150 kilojoules per mole. Then subtract our temperature, which is 300 Kelvin, times our delta S, which is negative 0.2 kilojoules per mole times Kelvin. And that's because I divided it by 1,000 to get it into kilojoules. So T delta S comes out to negative 16 kilojoules per mole. Then I take my negative 150 kilojoules per mole and subtract the negative 60. So I'm going to end up with a value of delta G at negative 90 kilojoules per mole. So in this specific case, where we have negative and negative, and we say, according to the trend, that this is only going to be thermodynamically favored at low temperatures, in this case, the term low is going to be anything less than 750 Kelvin. Because once you plug in, like, let's say 800 Kelvin to this equation, now we're going to have a positive delta G. Just keep in mind that when we say low or high, the definition of low or high can change, and it's all relative based off of the magnitude of delta H and delta S.